Okay, thank you. It's a pleasure to be here. So I want to start with some physics motivations, since this is a physics and machine learning meeting, before diving into the really algorithmic and mathematical details that are common to many of our problems here. So I'm a nuclear and particle physicist, and what I'm really interested in is understanding the structure of matter from the ground up, from first principles. So we have a beautiful theory in particle physics called the Standard Model of Fundamental Particles that describes the dynamics and interactions of the most fundamental constituents of matter, quarks and gluons. And I would like to understand how we go from quarks and gluons, not just to the structure of protons and neutrons, but to the structure of nuclei, and see the emergence of all of the complexities of nuclear physics from the ground up. So this is important, not just to understand the structure of matter at the level that we interact with, but in searches for physics beyond the standard model, physics beyond what we understand. So many of these searches for physics beyond the standard model are what we call the intensity frontier. We're looking for very rare interactions. Things like searches for direct interactions of dark matter with nuclei here on Earth. Things like trying to understand the nature of neutrinos. These are fundamental particles. We don't know their masses. We don't even know if neutrinos are their own antiparticles or not. The experiments seeking to determine this are what we call intensity frontier experiments. They rely on understanding the structure of nuclei at a very precise level. So understanding nuclear physics from the ground up is important for its own sake, and also to understand and find physics beyond the physics that we understand at the moment. Okay, so the big challenge in doing this is understanding the strong interactions. So that the strongest of the four fundamental forces, it binds fundamental particles together, quarks and gluons together into protons and neutrons. It binds protons and neutrons together into nuclei, also responsible for forming other types of exotic matter. The problem is that this theory is very hard to solve, very hard to extract properties from quantum chromodynamics or QCD analytically, because it's a non-perturbative theory. There's no, at low energies, there's no small parameter that you can expand in and therefore make a perturbative approximation to some order. So the only solution we have is numerical. So to do numerical studies of physics at this level, of particular of the strong interactions, we have to discretize the theory onto a four-dimensional space-time grid. That's 3 space, 1 time dimensions. And then we have to solve the theory on this discrete finite space-time that we put on a supercomputer, right? So essentially this boils down to having to do a very high dimensional integral very precisely, an integral in something like 10 to the 12 to 10 to the 20 dimensions. This is a massive computational task. We evaluate this integral by importance sampling. So you sample the most important contributions to the integral more than the less important contributions. You can think about this in the sense of even just an analogy to quantum mechanics. We know that the classical paths dominate in quantum mechanics, so you sample those more often than the less dominant but still important less classical paths, right? So this is a hugely computationally expensive task. So in the United States alone, trying to solve standard model interactions takes more than about 10% in the last 5 years, 10% of open science supercomputing in the United States. So algorithmic acceleration is, of course, extraordinarily valuable when you're really maximizing what's possible computationally. And many of the problems we need to solve in order to pin down physics beyond the standard model are currently still computationally intractable. So algorithmic acceleration is really the name of the game, and that's why I'm interested in machine learning for these problems. So some of the key computational tasks that we need to accelerate. So the first one is to generate what are called field configurations, samples of the background quark and gluon dynamics. This is the important sampling part. This takes leadership class computing. You can think of scales of 100,000 cores in sort of one stream, or thousands of GPUs at a time, tens of teraflop years. And this being the workshop that it is, this generating field configuration is really what I want to focus on in this talk. The other steps of the calculation, which if someone has great ideas of ways machine learning might accelerate these other parts of the calculation, I'd love to talk to you as well. Very large sparse matrix inversions that have to be distributed over hundreds of GPUs, so slightly smaller scale calculation, but it has to be done many more times. And contractions, which is exactly what it sounds like, tensor contractions, which again is smaller scale on the order of just a few GPUs at a time, but has to be done millions of times more often than the previous larger computational steps. Okay, so hugely computationally demanding, important both to understand the physics we know and to pin down the physics we don't know. The computational cost grows exponentially and factorially badly in various ways as we try to scale up the size of the system. So this is something that we can't beat with just growing computation. Okay, so to boil down this key problem of generating field configurations into its algorithmic core, what we need to do is generate configurations, I'm calling them phi, which you can think of as distributed across a space-time lattice, so there is some spatial structure in some of the degrees of freedom, according to some known probability distribution, this e to the minus s, where s is an action that encodes the quark and gluon dynamics in this theory. Right? So I need to sample these field configurations, which you can think of on this grid as being represented by roughly 10 to the 10 links, a link joining two nodes on this lattice, where each link is a 3 by 3 complex matrix with unit determinant, so SU3 matrices. So I need to sample something like 10 to the 12 double precision numbers in this structure, according to a known probability distribution, where I know the probability distribution up to the normalization. And if I can do this efficiently, then that is a significant part of the computational cost of these calculations that we can accelerate. Okay, so this is done typically before the sorts of machine learning methods that I'll talk about using hybrid Monte Carlo, also known as Hamiltonian Monte Carlo. So the idea is that you couple molecular dynamics with Markov chain Monte Carlo. You start with some configuration, you inject some momentum by, so here's our field configuration. We have a Hamiltonian determined by the action. Here's a conjugate momentum, which is something that you sample from a Gaussian. You inject some momentum in the system. You integrate the equations of motion over some trajectory and you update your configuration. And then because we have numerical integrators, so energy non-conservation, this is not exact, so you do an accept-reject step to restore your correct probability distribution at the end. So you propose updates, and then you accept-reject them in your usual Markov chain Monte Carlo. The problem with this is that you have to have very short integration trajectories for high acceptance, meaning that you end up with correlations in your stream of generated configurations. And so if we think about this Hamiltonian or hybrid Monte Carlo process, you have first some sort of a burn-in process. You update configurations from some hot start or a cold start, some number of times until you reach equilibrium. Then you can start sampling. But if your configurations are correlated, then you have to sample some number of times before you've changed physics, before you have an independent sample. So there are really first this burn-in time, and then you can only sample every nth configuration if the correlation length is n. And so both the burn-in time and the correlation length are really dictated by what's called this autocorrelation time, how correlated each sample in your chain is. So the problem is that this autocorrelation time diverges in key limits that we have to take. The problem is really that in our case, this critical slowing down can be thought of as just a lattice spacing issue. So we're discretizing our theory, in this case the theory of the strong interactions, onto a grid, right? And to get back to continuum physics, you have to take the limit as the grid spacing becomes small. But if you think about this Hamiltonian or hybrid Monte Carlo procedure, really the updates are close to local. They're sort of iteratively expanding, which means that if you want to change physics on a fixed physical length scale, something like a proton size, as you make your grid smaller, the number of updates you have to do to reach that fixed physical length scale grows. Right? And in the limit, as the lattice spacing becomes 0, you have to do an infinite number of updates to change physics on that scale. So this is what we call critical slowing down. It's really the same problem as critical slowing down in many other contexts. Essentially, it means that in this limit that we have to take to get back to physical calculations, our computational cost diverges. So we can measure this autocorrelation time. I'm going to call it tau naught int. You can measure it basically by measuring how correlated some observable is as you move down your chain. Usually we parameterize this autocorrelation time with some critical exponent. So L is like the size of your box to some power, and we talk about whether that power is large or small as how bad the critical slowing down of the problem is. Here are just various physics quantities that you might be interested in calculating. The left-hand side of this horizontal axis here is the critical limit, the limit we have to take. You can see things diverge on a log scale as we go down to the fine lattice spacings. So this is really is critical slowing down, but it's also a critical problem for us in achieving some of our physics goals. So I'll talk about two approaches to try to overcome this critical slowing down issue with the help of machine learning. Really focusing more on the second one, which is generative models for the theme of this workshop, but I'll talk first a little bit about multi-scale algorithms. A key thing for us is that what we're doing is a rigorous approach to studying the standard model. So to studying the quantum field theory, which is defined by the standard model of particle physics. So to us, it's not acceptable to introduce uncertainties into our sampling. So we're only going to consider methods that allow us to rigorously preserve the fact that in the right limits, we are studying the quantum field theory that we know. So that's a big constraint for us. Okay, so talking first about multi-scale algorithms. So there is a way to overcome this critical slowing down procedure. As I said, the slowing down happens as we take the lattice spacing to be very fine. The slowing down in the updating procedure. So if we had a method by which we could map from a fine configuration to a coarser configuration and back again, while preserving most of the topology of this configuration to a good extent, then what you could do is you could say, what I really want is a fine simulation. I want to sample over the fine degrees of freedom, but you could coarsen it. You could do your usual hybrid Monte Carlo, Hamiltonian Monte Carlo updates in the coarse space. Then you could re-refine. And of course, you wouldn't expect this to be exact, but if you've generated independent configurations here, you can now rethermalize, do a few steps in the fine space to restore the exactness of your distribution. And you can overcome this critical slowing down problem by moving to ever coarser and coarser layers, doing the bulk of your updating there, and then re-refining down again. The problem here is that you have to know the matching parameters between your fine and your coarse calculations. Of course, one of the key things you need to know to do this Hamiltonian or hybrid Monte Carlo is the action that's dictating your probability distribution, which has some parameters in it. So you need to know the parameters of this action that encode the same physics at the fine discretization scale and at the coarse discretization scale. So this is really a problem of a renormalization group flow in this space, right? So how do you find out what parameters give you the same physics in two different simulations? Well, you could calculate physics in the two different simulations, map out the parameters, and find the matching places, right? The problem is that you'd have to do calculations in the coarse and the fine space to be able to map physics parameters. And we can't do calculations in the fine space because we can't sample from it efficiently. So it's computationally intractable. So then the question is, how do you match what parameters of the action encode the same physics in a coarse space and a fine space without being able to do calculations on the fine space? And so this you can phrase as a regression problem, right? Given a coarse ensemble, which might have come from a fine ensemble, or maybe even just a couple of fine configurations. Let's say you can afford to make a couple. Then you coarsen them. You can, in this case, throw away all these intermediate degrees of freedom, just leave the coarse degrees of freedom, and say, OK, what parameters in the coarse space could have generated these configurations? So this is really the same as a regression problem. So with the parallel to image recognition, you have an image, you want to find the label, right? We have some gauge field configuration, which is a very large tensor, 10 to the 12 real numbers, and we want to know what are the few real numbers that parameterize the action that could have generated that configuration. Okay, so this solves the problem to a good extent. The parameter matching can all be done on the small coarse ensembles. So all you need to do is generate coarse ensembles and match their parameters, so all of your training data can be in the coarse space, right? You never need to train in the fine space because you want to say, if I have a coarse configuration that fell from the sky, what are its parameters? It doesn't have to be exact, so you correct for the mismatch by rethermalization steps in the fine space. Ultimately, if your matching is bad, then what you're doing is going from your fine space to a coarse space, doing updates there, that when you map back down, you're now in a different probability distribution to the one you want. So when you do your rethermalization steps, it will take a long time to rethermalize, and your algorithm will be slow. You will have gained nothing by moving up the level and then coming down. But you won't be wrong. Yeah?
So you're using regression to invert, because you're kind of inverting the function that maps from fine to coarse. So you invert, but isn't that a ill-defined inverse problem?
So we're not trying to invert the function. So I'm not asking what is the map that takes me between fine and coarse or coarse and fine. I'm saying if I have a coarse ensemble, what are the parameters? So it really is a regression problem. So technically, in this renormalization group flow, in the quantum field theory perspective, you're introducing a whole bunch of irrelevant operators, and if I don't know what they are to match them, what I'm doing is projecting down onto the orthogonal subspace closest to the action that I've parameterized that I'm matching to.
So it's like a regularization. Okay.
Exactly. Okay, so this is a nice problem. It sounds a lot like image recognition, assigning labels to things. The only problem is the data scales and data structures are quite different. So each of our samples, each of our images, if you like, is defined by, say, 10 to the 9 numbers at the coarse scale. Typically, 1,000 of them is a good size sample. So you can already see we have this sort of inverted data hierarchy where our number of degrees of freedom per sample is far larger than the number of samples I might have for training, which is problematic. It's only the ensemble of these things, so the collection of them, that has any sort of physical meaning, because I'm sampling from a probability distribution. And any single sample could have come from other probability distributions with some probability, right? So it's only on average that this has meaning. It's long-distance correlations that actually define the physics on these samples. So it's not in an image, some subsection of the image, you might have a nose or an eye, right, that has some meaning on its own. For us, it's really the long-distance structures that are the key. And we also have some interesting symmetries. So, of course, we have rotations, translations in 4 dimensions with boundary conditions. But we also have what's known as gauge symmetries on these configurations. So remembering that each link on this lattice is a matrix, we have a matrix transformation where you multiply the link on either side by another one of these 3x3 matrices with unit determinant, and do this transformation across your entire configuration, so the gauge transformation. So physics is also invariant under these complicated transformations. Okay, so the simplest approach to this sort of a regression problem is to say, okay, let's try solving this with a neural network, and let's just ignore all of the physics symmetries. Yeah.
Your gauge degrees of freedom, are they going to hurt you here? Because you have this kind of arbitrary, because the physics only depends, it's not the gauge invariant, but the representation you're sampling has a bunch of gauge parameters in it, right?
Yeah, that's exactly right. So
if you go coarse and fine, you might come back to a different gauge or something like that.
So, I mean, the physics is gauge independent, so changing gauges is irrelevant. But there is something here that will come and hurt us, and you're about to see this. So the simplest approach of ignoring the physics symmetries, what we're going to see is that you end up caught by these unphysical degrees of freedom. And then you have to actually put the physics symmetries back in to undo that. Basically because this is such a large symmetry group that there's no way of trying to learn it, even doing something like data augmentation, because the gauge symmetry is such a huge symmetry group. So the very simplest thing we can do is say, okay, let's pretend that the inverted data hierarchy doesn't matter, that there's some hope of getting a good result, even though each sample has far more degrees of freedom than the number of samples I have. And so my neural network has far more degrees of freedom than the number of training samples I'm going to have, which you expect to fail miserably, right? So you throw it into a fully connected network, we expect terrible overfitting. To give you an idea of what this data structure looks like, so in a sort of simplified version of this theory, we can think of just having 2 parameters. Some parameter related to the lattice spacing, that's how coarse or fine our sampling is, and some parameter related to the masses of our fundamental particles, the quark mass. So you can think of the action as being defined by these 2 parameters. If I want to generate training data in this space, the coarse space, right, I'm saying a coarse configuration falls from the sky, what are its parameters? What we can do is generate training data, but unfortunately, because the data is generated by this hybrid Monte Carlo updating procedure, you can generate a lot of data at one set of parameters somewhat efficiently, but you can't generate data nicely distributed in this space. So we have a very spiky training data distribution with, say, 10,000 samples at each of these points and nothing in between, which again is a challenge. So we say we've generated 10,000 independent configurations at each of these colored points in this parameter space. By independent, I mean they're separated in the stream by enough that they're independent by every measure of physics observables. But we know which are the most correlated physics observables. They're independent according to those measures. So if we actually train on this and then make predictions from this neural network that we expect to have failed spectacularly, you find these little blobs here are my 2 standard deviation confidence intervals for predictions from validation data on this data set. So this sounds wrong, right? We had something which should be overfit, and yet we get good predictions. So the next thing to do is to try to generalize. So now generate data at some intermediate set of parameters. And what we find is that this fails spectacularly, as it must. You get regression back here to roughly the mean of all of the data. Okay, so what this is saying, this is not possible that this performs so well if the configurations that I used for training and validation were actually uncorrelated. So the neural network has uncovered some longer correlation length in the training data and validation data than any known physics observable. So just to emphasize this, we have a stream of generated configurations. We take training and validation data separated far enough in the stream that it's independent according to every measure that we know. But if the network succeeds for validation configurations from the same stream, but fails for different streams or interpolated parameters, then it's identified a feature with a longer correlation length in the Monte Carlo stream than any known physics observable. You can actually measure this correlation length. So you can train a network to discriminate. You can take the same architecture as the network that we used, but train it to discriminate between configurations at the end of a chain. And of course, it will discriminate less and less well as you go further along the chain. And you can map out that discrimination as a function of length of the chain and actually measure this autocorrelation time. So we can compare this autocorrelation time that the network has found to the maximum of any known physics observable, and it's significantly larger. So this, of course, was initially puzzling, because if the configurations are actually correlated, that would be very bad if they're correlated by any physical measure. So what it turns out is that the network has identified the correlation length in the gauge degrees of freedom, the irrelevant degrees of freedom. And the fact that those update slowly along your Markov chain is the very reason that the Markov chain works so nicely, because if it was spending all of its time moving around in the irrelevant degrees of freedom, it wouldn't be as efficiently changing the relevant degrees of freedom and sampling the space. So this is actually very nice. We could measure for the first time the autocorrelation in the gauge degrees of freedom of your HMC algorithm. And in some sense, a longer autocorrelation time here gives you a more efficient HMC algorithm. Okay, but this wasn't the problem that we were trying to solve. So
this is purely a numerical artifact, right? So you introduce these additional degrees of freedom in your simulation, but they're irrelevant for the physics, and the network finds this correlation.
Yeah,
it's not physically relevant, this correlation time, or is it?
No, it's not. It's not a physically relevant correlation time. Any physical observable should be gauge invariant. Yeah. What it is a measure of the usual algorithm that we use, which is what we use to generate the training data, is how efficiently that's actually moving in our parameter space. If it were moving very fast in the irrelevant degrees of freedom, it wouldn't be as efficient an algorithm. So
this sort of correlation would not be experimentally measured?
No.
It's purely simulation thing?
No, certainly not. It's a correlation in the sampling. Right.
Ideally, in the limit, ideally you want the gauge degrees of freedom to stay fixed. You're not controlling them directly, but in an ideal case, you want them to be fixed to increase your autocorrelation time.
Yeah, exactly. If you could make that larger, you'd think you would have a more efficient HMC simulation. Okay, so to solve this problem of multi-scale regression, however, the obvious thing, of course, is to use symmetry invariant features at some level. Try to build the symmetries of the problem into the network, thereby reducing this massive extra symmetry space. So you can do that by forming products of these links around loops. They're called Wilson loops, or also correlated product of loops at various scales. Because we know the long-distance physics is relevant in these simulations, you know that products of these things at some long-distance scales are likely to be important features. So you can reparameterize all of your data in terms of the short and long-distance correlations, product of these loops at various distances. Then you can use, again, past the first layer where you're constructing various symmetry invariant features, you can use something like a fully connected neural network, and you can do this exercise again. So here's the same data set. Again, we had this spiky training data, We have two parameters, one related to the lattice spacing, one related to the quark mass. And what you see on there, these ellipses, are again the two standard deviation confidence intervals of validation data on these sets. So you'll see a few interesting features. You see that they're all elongated in the same direction. And this actually makes sense now. This is the direction that's closest to the line of constant physics in the simulations. So along those lines, it's hardest to distinguish because those are the lines closest to constant physics. You can make predictions on new data sets. You can go much more closely spaced than your training data, remembering that this was very spiky data that really didn't cover the space very efficiently. You can go in between, and you still, or you can go outside, and you still have nice predictions. You can actually calculate these minimum size of these confidence ellipses because, of course, what you're sampling from is a probability distribution, and any one configuration could have, with some probability, been generated by parameters with nearby values. So if you have a set of configurations, you can calculate the size of the ellipse that should define the most probable region of your simulation parameters. Okay, so this is success. The question is, how does this compare with other approaches? If I'm already forming symmetry invariant things, what if I just do something other than machine learning to try to determine the parameters from those? So to test this, we made very closely spaced ensembles. Our training data was, for example, here and here. This is much more closely spaced, and specifically along the line of constant physics, so this should be the hardest test case for the network. You can do a principal component analysis in this space on all of the features that the network was allowed to construct in the first layer. And you can see the two sets, which were offset in this space, can be distinguished by the dominant few eigenvectors, but within each set, you can't really distinguish them. You can do more concrete tests rather than just showing you the histograms of how well these can be distinguished. And you can compare them to the neural network predictions, which are much better distinguished than a principal component analysis. So the nonlinearity is actually helping here. And we have accurate regression even at these very fine resolutions when we trained using very coarsely spaced data. Okay, yeah?
What are these contours right here?
These are two standard deviation ellipses from taking validation data and asking for the predicted values of parameters. Yeah. Okay, so this is a proof of principle for using this multi-scale method. It works nicely. The downside is that you still do need training data in the coarse space. So we had to do all of the training in the coarse space. We had to grid out the parameters. In doing that, you need to know roughly where in parameter space your fine ensemble should go to. So there are still challenges involved in using this method, but it's very nice. We're able to actually do regression on data with 10 to the 12 degrees of freedom. Okay, so another approach is to say, well, let's not try to improve hybrid Monte Carlo, maybe by doing this coarsening and refinement and trying to accelerate. What if we try to use a generative model directly to generate these very large gauge fields? So this is work done with two excellent graduate students at MIT, and Michael was an undergraduate who's now at NYU as a graduate student. Okay, so the problem is again the same, right? I want to generate these field configurations with a known probability distribution. So just for convenience, I'm going to use this here, these two-dimensional, it's a scalar field theory, meaning there's a real number at each site on the ladder so we can draw nice pictures as my examples here. I want to generate these images with a known probability distribution. These are actually genuine log probabilities for these various images. You see that just completely random noise is very unlikely, but when you have some correlations at some characteristic scale, these become the likely images that we want to generate. So this has, of course, parallels with an image generation problem in other contexts. We want to generate more of the likely configurations, less of the unlikely configurations, with the difference being that we want to generate very specifically more of these and less of these, but these should still occur. Whereas if you're generating faces, of course, I think you never want just noise. Right. Okay, so the setup we have is that the probability density can be computed for a given sample up to normalization. So given a sample, I can tell you the probability density. The physics distributions still have precise symmetries. So we have the translation, rotation, reflection, and the internal gauge degrees of freedom that I talked about before. Those all still exist. So if you do a gauge transformation on your configuration, that other configuration should have the same probability of being generated. Okay, and the data hierarchies are still challenging, so we have a very large number of degrees of freedom per configuration and few configurations available typically, so we are not going to use any training paradigms that rely on existing samples from the distribution, because if we could generate that training data, we would have solved our problem. Okay, so we approach this using generative flow models, which I think we've already heard about at this workshop, where the idea is to go from some easily sampled distribution via some change of variables to an approximation of the distribution that you're actually interested in, right? Preferably an invertible approximation with a tractable Jacobian. For us, this is critically important. So for each sample, I can tell you the probability density that it should have. If there's a tractable Jacobian and we have some easily sampled distribution here, then you can take your easily sampled distribution and compute the probability of that final state with which that sample was generated, and you can compare the two, right? Okay, so this mapping is made up of many simple layers that are composed to produce the mapping that we're actually interested in, where for us we used real non-volume preserving flows in this example. So we're doing an affine transformation of half of the variables. So if you think about this case of the two-dimensional field theory with just a real number at each site, taking a checkerboard pattern and splitting half of the data into two streams, where half of the data is transformed by the other half in each step, and then swapped so that you end up with a nice triangular Jacobian. Okay, so each of these layers here has a scaling and a translation, which are parameterized by arbitrary neural networks. So the scaling and translation gives us this squishing and the stretching of the density, which is very convenient. Transforming half the variables at a time lets us actually build in some physical intuition. In this case, for the scalar field theory, a checkerboard pattern is pretty convenient. Going to gauge theories, you want to think more strongly about exactly how you choose the half of the data to transform such that you maintain the gauge structures. Okay. So again, the target distribution is known up to a normalization, so we train this thing to minimize a shifted KL divergence. We subtract log z so that we don't have to compute the unknown normalization, which just means that the minimum of the loss is minus log z, whatever that is, rather than 0. And by choosing the KL divergence in this direction, it's of course asymmetric, it allows us to sample with respect to the model distribution to estimate the loss. So we never need to actually sample with respect to the true distribution, only the model distribution, meaning that we can do self-training. So we can sample from our easy-to-sample distribution, feed it through in some batch. We estimate this stochastically in some batch. Then you can calculate the probability density from your model of each sample in that batch, and also the true probability of each sample in that batch, and you can compare the two. And then you can optimize to make those as close as possible. Okay, so then the other part is, of course, that I said this all needs to be exact. So what we might generate, if we have a good model, is an approximation to the distribution that we're interested in. But we need to make that exact again. So what we can do is feed this all into a accept-reject step, where we define the acceptance probability by the ratio of p tilde here is our model probability distribution, and p is our true probability distribution, since we can calculate both. So we define the accept-reject with the ratio of the true and model probability distributions. And so what we have is a trivially parallel generation. All of the samples are generated completely independently. In our case, this is very important. It means we can farm it out over very many different GPUs. And then once they're generated, you throw them into a chain where accept-reject is based on your sample and the previous sample in the chain. Right? So this means that you can have parallel generation, but when you put them back together and compose them into a chain, you can still guarantee that you get the right probability distribution in the infinite statistics limit. Okay. So a summary of this approach is that we parameterize this flow from some easy-to-sample probability distribution to an approximation of the distribution we want using real non-volume preserving coupling layers. Then we train, and so the training is done by drawing samples from the model, computing loss, gradient descent, and iterating. So there's no training data that ever needs to be done, ever needs to be supplied in this context. you can calculate you can take your trained model at any stage, take samples and compose them into a Markov chain, and you can calculate the acceptance probability. And you can use that as a stopping criterion, because that's a measure of how close your distribution is to the true distribution. If you have 100% acceptance, then your sample distribution is, you're sampling from the true distribution. If you have lower acceptance, then you're sampling from an approximation of various levels to your true distribution. So we can choose some accuracy, some acceptance rate as a stopping criterion, save the trained model, then you can sample completely parallel, trivially parallel from that model and compose them into a Markov chain. Okay, so a practical application was we applied this to scalar lattice field theory. So that is, you have a real number per site of a lattice, which is just a slightly less complicated toy model for the model we actually want to do, where we have these gauge links, these matrices on each link of the lattice. You have an action which has some quartic and cubed terms of the sites of the lattice, and also something coupling neighboring sites, which is why this checkerboard pattern was a particularly useful one for this example. We chose different lattice sizes with parameters tuned for an analysis of critical slowing down. So we chose parameters along that critical line. So where sampling becomes, by traditional means, more and more costly as you move along that critical line. Okay, so again, taking some easy to sample distribution, in this case of a scalar field theory, you can take uncorrelated Gaussians. You can just take Gaussian noise on this lattice. You flow it through these real non-volume preserving couplings. So we used something like 8 to 12 of these coupling layers, where each coupling layer had 2 neural networks, each of which had 2 to 6 to 10 sort of fully connected layers with 100 to 1,000 hidden units in each of those layers. So this is a fairly sizable implementation of this sort of a flow algorithm itself, even for this small toy model. We trained using the shifted KO loss, various optimizers, but then we had the stopping criterion was a fixed acceptance rate in the Markov chain when we recompose these samples into a chain. Okay, so we can try to do the same thing you might like to do with images and look at the samples. Do they look like samples generated using other methods? So on different size volumes, here's a local updating procedure, here's usual hybrid or Hamiltonian Monte Carlo. Here's our model trained to a 50% acceptance rate, and you can see, okay, the samples are different. They're not all the same. The correlations look broadly at the right scale, but of course we want to make this quantitative. So the first thing we might be interested in is how do the rejection runs compare? So I'm sampling this in a trivially parallel way, and then I'm composing into a chain. And I'm doing accept reject, and say I've chosen my stopping criterion to be 50% acceptance. But is that 50% acceptance accepting every second configuration? Or is that 50% acceptance have long runs of rejections followed by long runs of acceptances? Right? This is important for how robust your model is. And we find that the rejection runs are completely consistent with those from hybrid Monte Carlo tuned to the same acceptance. In fact, so the machine learning models are here, the not red ones, the blue, the gray, and the orange. And if anything, they have slightly shorter rejection runs than hybrid Monte Carlo tuned to the same acceptance. Yeah?
Because your chain is arbitrary, you looked at shuffling it and seeing if the behavior changes. Because it seems like it's not a Markov chain, like it's actually sequential.
Yeah, it's not, but as soon as you choose an ordering, then you lose your guarantees of correctness. So there's probably, from some samples, you could compose them into an order that has a higher acceptance than any other order, right? But in doing that, you then lose your ability to prove that this converges to the right distribution in the infinite statistics limit. Yeah. But you're quite right. So each sample depends on the previous one only in the sense of whether it's accepted or rejected. Yeah. Of course, we can also compute physical observables. So here are some physical observables computed on each of the size lattices. Obviously, the error bars are tiny. They agree even with tiny error bars. And we've pushed this to ridiculously high levels of sampling to see if we can find disagreement, and we don't. So physical observables match, as of course they must if you're sampling correctly. So So if this had failed, it would tell us that our distribution is, matching. If you think, you're trying to reproduce like a Gaussian in the space that I'm waving my hands in. If you reproduced maybe the central part, but then just chopped off and didn't have the tails, then you could expect maybe a high acceptance, but you wouldn't expect physical observables to match in the large statistics limit. Since if you're sampling, if your map is 1-to-1 and every sample in the initial space has some probability of being sampled, you shouldn't have this happen either, but you could think of pathological edge cases where it might happen. So we don't have those. Okay, the other question is, how about uncertainties? Are we really generating independent configurations? And yes, the uncertainties in physical observables follow statistical scaling. So they reduce like square root of n as you increase the number of samples. So there's not some measure by which we're sampling configurations that look more like themselves in terms of physical observables than they should. So this all checks out. And we can, of course, do this sort of key comparison of critical slowing down. So what I'm plotting here is the autocorrelation time, tau, versus the side length of the boxes. And if you remember, these boxes here were tuned to be along a critical line. And you can see that critical line here. Using a local updating procedure, you can see that the autocorrelation time increases exponentially badly as you go to the right here in these plots. So each of these sets of data is for a different physics observable. The autocorrelation time can be different for different physics observables, so you can measure it for each one. For hybrid Monte Carlo or Hamiltonian Monte Carlo, again, you see these critical behavior, critical exponent growing as you move along the critical line for every observable. But for our ensembles generated with this flow method, you see that there is just no critical slowing down at all. And of course, that had to be the case because we're generating them independently. And the only way they get correlations is by being accepted or rejected based on the previous configuration. So the only way this would fail is if the network is somehow generating samples that all look like each other in some well-defined way. Okay, so you'll notice a few things in this figure. I have two lines here. One for models trained to 50% acceptance, and one for models trained to 70% acceptance. So of course, as you train further, you accept more often, and therefore your autocorrelation time decreases because you're accepting more often. So you can derive theoretical bounds on your acceptance rate, which are shown here, based just on how well you train the model. Okay. So this yes?
May I ask you what's the computational cost that you have between training a model to 50% acceptance rate and 70%? Is it like a lot or?
Yeah, so in these cases it was considerable, but in this proof of principle it was also, it's hard to quantify because we didn't exactly set, this is the training prescription and let it run. It was tweaked along the way, the parameters and what optimizer we were using got changed at various points, so making a quantitative comparison like that for exactly these ensembles is hard. What we find is that, yes, it is quite expensive to train things more, and of course the tipping point depends not only on the training cost, but on what ensemble you ultimately want to generate, what sides of the ensemble, because the training cost is amortized over the cost of the final ensemble you want to generate. So whether it makes sense to train to 50% or 70% depends on whether you want 1,000 configurations out at the end or 10,000, right? Which is also, a very natural question to ask is, are we moving the cost of critical slowing down into training? How much more expensive is the training for each of these models along this line? Because if that's growing exponentially, you could say, well, you've just moved the exponential cost from one place of sampling into the cost of training. And the answer to that is, again, it does get more expensive as we move along. But that cost is a once-off upfront cost. And it's amortized across however many configurations you want to sample from, as opposed to an exponential increase in the sampling cost, which, of course, no matter how many configurations you want to sample, you have that exponential growth. So, yeah, so this has no critical slowing down. Whether or not it's worth doing depends critically on how many samples you actually want and on and where you should stop depends critically on how many samples you actually want. Yeah. There are some other nice sort of related tangents to that, is that if you have a trained model, even if it costs a lot to train, if you can retrain to nearby parameters, then you can generate another ensemble at nearby parameters without all of that upfront training cost. So what we've found is actually that you don't just get an ensemble at fixed parameters out of this. Your upfront training can give you ensembles at a range of parameters in your space. And so it can be, even if this would cost many times as much as a single ensemble to generate, it could still be the most efficient thing to do. Yeah?
Since you're at that slide, I wonder if, since you don't know maybe how many samples you want, you could just alternate training and sampling to optimize your cost by kind of optimize schedule from the point of view of the poles. Like for the poles, you're training more, sampling more.
Yeah, so when you start, proving that you reach the right probability distribution becomes harder when you're changing your model between samples, right? But you could think about doing something like that. Quite often we do know for a target physics calculation what number of independent configurations we need. So in that sense, if you know how many configurations you want for a target physics study, you can also calculate at what point it becomes viable to do this. We've thought about that. The other thing we've thought about is alternating sampling this way with traditional hybrid Monte Carlo updates. And this method gives you a very nice way of sampling into multiple, say, vacua of a physical system in parallel, because you're not, one of the problems with HMC is that you get stuck moving around some. If you have like a peaky distribution, you get stuck in one part of parameter space, and this is a nice way to sort of sample into many. But again, if you want to guarantee your cost, you could do like a broad sampling into your space and then use other methods like hybrid Monte Carlo to move within those regions as well. So there are various ways of trying to combine this with other methods to make it more efficient. Yeah. Yeah.
So how well do you represent the real probability distribution you have? Do you know if it's always kind of approximate? So is that a worry for you?
Right, so it is always approximate. The very fact that this is 50% or 70% acceptance gives you a pretty quantitative measure on how well our probability distribution is approximated. But no, that's not a worry, because you can prove that doing accept reject with this ratio of your probability density to your model probability density gives you, in the large sampling limit, the right probability distribution.
So there's no parts of phase space that you might not be covering?
So you could imagine pathological cases where that might happen. The fact that we can push this to embarrassingly high statistics and see no difference between all the various sampling methods on physical observables is pretty good evidence that that's not happening. But there is something, especially as we go to more complicated theories, that we have to worry about and find ways of quantifying. Yeah, but this is also true for any sampling method. So also for hybrid Monte Carlo, you have this has precisely the same guarantees of correctness as the hybrid Monte Carlo sampling method that is normally done. That does not mean that either is foolproof, right? Yeah. Okay. So the next step, so the target application is, of course, as I said at the start, to be able to solve some of these currently just computationally intractable physics problems. We want to calculate the reactions in Big Bang nucleosynthesis in the first few moments of the universe. And we can do at the moment the first step in that chain reaction, and then the others are just computationally intractable. So to do that, we need to scale this. We need to go to 4 dimensions, where the grids are something like 48 cubed by 96. We have to have gauge theories, so instead of just real numbers at each site, we need to take links of matrices. So we have to scale the dimensions, the degrees of freedom. We have to deal with the gauge symmetries. So number of dimensions is not a problem. For this scalar field theory, we've moved to larger numbers of dimensions. It becomes slightly harder to train, but there's no theoretical obstacles, and this seems to work. These are actually samples generated on 3D. For a phi to the 4, a scalar field theory example with critical behavior. Scale the number of degrees of freedom. So when we had our neural networks parameterized, they were fully connected neural networks. This doesn't have very nice scaling properties with number of degrees of freedom, but we've found that we can look at convolutions and having a hierarchical structure. And then if you want to keep the parameters the same but scale the volume, we have very nice transfer training results. This works very well. Of course, that doesn't work along the critical line. You have to do the small volume at the same parameters of interest, and then you can use transfer training. The very significant component we need that we're working hard on is methods for gauge theories. So how to deal with the gauge degrees of freedom in these structures. So, various options like, can you fix the gauge degrees of freedom and then keep your flow entirely within a gauge fixed space? Or can you guarantee that you're moving from one gauge to another and have sort of a gauge fixing at either end? Or can you have other ways of building in those gauge degrees of freedom such that your number of degrees of freedom don't explode and become intractable again? In principle, you can also brute force the gauge degrees of freedom, but then your number of samples you have to take grows significantly. Okay, so in accelerating gauge field generation, there's now a couple of nice proofs of principle for this field, both with this multi-scale matching and generative models to replace HMC. And I think this is extremely promising, that there might be possibilities of algorithmic acceleration using various machine learning approaches. There are also other very significant computational challenges in this field that no one has yet applied machine learning to, and where some algorithms, particularly reinforcement learning algorithms, might work efficiently. So there's a problem not just of generating the gauge fields, but then of extracting physics from the gauge fields. And there's one particular part of this problem where you have to compute an operator which couples to the physical states of interest. So it has the same quantum numbers as the states of interest. And if you're interested in, say, the proton mass, you want this to have a strong overlap onto the proton and less overlap onto excitations of the proton, heavier states. You get rid of all of those excitations by waiting a long time in what's called Euclidean time. They die off. This is exactly what you can see here, this exponential contamination. That's all slightly by the by. The point is that if you could design a better operator, you could remove this exponential contamination. And you can see these points here have much smaller error bars than these points here. If you have no exponential contamination, instead of trying to sample in a window like this, you can sample in a much earlier window and has a potential for an exponential removal of a noise problem. So this sort of design of an optimal structure is something that might be suited to reinforcement learning. There are other interesting approaches with analysis. You end up with circular statistics problems in a noise region of these calculations that are things that might be tractable. So these are things I'm hoping to hear more about at this workshop. But I think the upshot is that accelerated algorithms really have a huge potential to enable first principles nuclear physics studies. So if we can accelerate those algorithms with machine learning approaches, that could be scientifically immensely valuable. Thanks.